Hello everyone, I hope you can hear me.
Yes, sir.
Okay. So let's start the last session for the course. So this session we'll be discussing a few things based on week 12 lectures. I'll share my screen. I think you can see my screen now. Okay, so let's start. What what was the topic of the last week lectures? Anyone? So for the last week, it was mostly focused on applications of computer vision. Uh, Most of the lectures in the previous weeks were focusing on the basics, but that is the fundamentals part. But week 11 and week 12 were focused more on the applications part. So it started with a gesture recognition. So can anyone tell what is gesture? Anyone? So when we express any thought or feeling, then that's called as a gesture. Well, this definition is also given in the class. I'm using the same definition, but yeah, it's generally given through probably through face or through any part of the body. And then we can make use of such gestures to get uh, what someone is trying to convey. So one of the famous ones are the hand gestures, which many people who cannot speak use such gestures. Okay, so of course there are many applications to gesture recognition which were given in the class. I'm not pointing those things again. But gesture recognition helps you to detect many things. Probably, for instance, in video surveillance, that if something is going wrong, they can detect it easily. Or, or maybe you want to get the emotion of the person, then you can also use the gestures to get an idea of how the person feels. Okay, so of course, this most of the gestures are can be sensed through different devices. Since we are in computer vision course, so we'll mostly use cameras and not the other things. You can also use motion sensors, but motion sensors have their own advantages and disadvantages, and cameras have their own disadvantages and a few advantages as well. So one of the basic disadvantage with cameras is that if there are sudden changes in light, well, cameras will still detect it. The point is the algorithms that we make to process such video sequences or the image sequence is not really robust. We still rely on a good amount of heuristics to make sure that we are invariant to many changes like lighting, or maybe if there is some sort of distortion, we just tend to make sure that we are correcting it heuristically in most of the practical scenarios. And cameras are, of course, generally costly than the other devices. If you really want a high definition camera, then it costs very high. And of course, there are many details you can miss based on how far the image is captured. That means how far the object is there from the camera. So that's why it's not trivial to use image sequence to get the gesture recognition. Okay. And there are, of course, different types of gestures that were discussed in the class. Uh, as I said, hand gesture is the most useful one because we generally tend to use gestures in our hand with our hand in our daily lives. Yes, there are many challenges as one of them, as I said, that if there is illumination variation or there is an occlusion, you can probably not detect where the gesture is happening. And if even if you detect, then there might be some ambiguities between different gestures, so it's not easy to recognize which gesture it is. Um, okay, so I'm not going into all the details that were discussed in the class, but the basic idea is to get a specific uh, pre-processing part is done. Like what um, the first part is you have to get the gesture video, and then once you get a video, you might want to enhance the video, for instance, do contrast enhancement to make sure that the next step is segmentation. So it helps during segmentation. So once you're done with pre-processing, you want to do segmentation of the specific object that you are interested in to find the gesture. For instance, if you are using hands for gesture, you want to first segment where the hand is in the video sequence, and then based on that, you want to check how the hand movement is there. So once you detected that there is a hand, and then the next thing is you might want to extract features of the hand and then track those features to get a pattern for which you want to for which can be used further for classification. Once you have the pattern, then yeah, it's a classification problem that given a set of feature vectors, how would you say which gesture it is from the class of known feature vectors? Okay. So of course there are various architectures that were discussed in the class on how to do gesture recognition. One of the one of the methods used is using depth data as well. So generally the depth data is obtained by using infrared sensors. So they are not so much variant to the human light that we see because they work in the infrared range. So they are very robust in the sense you can accurately get the depth. Once you get the depth, it's easy to do depth segmentation because similar values of depth belong to the same object in general. So once you are able to easily segment which part of the image you want to focus on, the next part is just to track how the depth data is changing. And some of the RGBD data is on available online. You can just check for it without looking. I mean, they're publicly available, so you don't have to search a lot. I mean, the first five results of Google search will give you a very nice data set on it. Okay, so yes, there are multiple features that were discussed throughout the course, and one of the features that you can use is shift features or surf features, or which are point-like features, or even the histogram of gradient features, which get the histograms of the segmented part of the image. Or you can do transform features like Fourier transforms or other transforms like wavelet transforms. All these features can be used to track during the gesture recognition. Of course, as soon as you change the features, the specific parts of the pipeline gets changed. You cannot use different features and expect that the pipeline for gesture recognition is same. Okay. So one of the methods that was discussed in the class to recognize a gesture is the dynamic time warping. Can anyone tell what is dynamic time warping? Anyone? Okay. Uh, so the point is, if, for instance, if someone wants to write the letter A, which is a gesture using their hand, the point is, if some people might write A in bigger size, some people might write A in smaller size, some people might rotate it in 45 degrees and write. So there are different variations to it. How to detect whether that person is writing A or not. So one of the ways that people used initially was dynamic time warping. So what they do is they have an initial data set from where they know the specific labels that okay, this specific gesture belongs to A. And once they have that label, they can just extract features from the specific gestures. That means for every point, for every frame, so you can take an example like this. For every frame, they'll have a set of features. So that is called as a template because that's coming from the data set. Now, if someone among you starts using the same software, it will also try to track your hand and get features from every frame. Once you have features from every frame, so now you have a template feature set, and then you have a new feature set. And based on the two feature sets, what you can do is you can compute distances between the two feature sets. And since it's a time series data, that means all features are dependent on each other. That means time if you have a feature at time instant t, then a t plus one, whatever feature you get, is dependent on the feature which is at time t. So making this thing into consideration, you can define a specific matrix using distances and the previous distances between the feature vectors among the two uh, cases. That is, first one is the template, and second one is the input from the user, and the second is also the distances based on the previous data and not specifically from the current time instant. So if uh, based on that, if the distances are small enough, you can use such dynamic time warping method. So when I say distance, uh, what is the general notion of a distance? What properties should a distance metric have? Anyone? Uh, so the first most important property is distance from a point to itself is zero. So this is called as constancy of self-similarity. So the self-similar, that means A and A are similar to each other. So it gives you a constant value which is zero. The next is the distance between 2 points will be the same whether you measure it from the first point or the second point. So that is the symmetry property. The third one is uh, very intuitive, that the distances cannot be negative, because what do you mean by negative distance? Displacements can be negative, but distances are always non-negative. Okay. And the last one is the triangular inequality. So if you have 3 points And if you measure the distances between 2 points and add the distances between the 2 points, it should always be greater than the third point. So this is the general triangular inequality. And there is another form of triangular inequality. This happens for any combination of A, B, and C. Doesn't have to be necessarily in this order. Okay. So the other form of triangular inequality, can anyone say? So this is what this says is sum of two sides of a triangle is greater than the third side. And the other one says is the difference of two sides of a triangle is always less than or equal to the third side. So both are equivalent. You can prove one from the other. You can try proving it. Okay. So this is coming from maths and not specific anything specific to computer vision as such. This is how the distance metric is defined. Okay. And of course, now this distance metric d of a comma b is actually being satisfied by many distance metrics. So one general way to write is maybe I'll so here a is a vector and b is also a vector. Both have the same length. And what we do is distance based on p norm is given as this expression summation of I equals to 1 absolute differences between the two vector elements raised to the power p, and after the summation you have to take pth root of it. So for p equals to 1, it is the Manhattan distance, which is coming from the L1 norm, and from p equals to for p equals to 2, it is the Euclidean distance, which is coming from the Euclidean norm. Okay, so yeah, we'll be doing an example of dynamic time warping in the class in the upcoming questions. So I'll not go through it into many details, but what we want to make sure that in time in the time warping cases is that whatever time warping you have the following properties. So this is dynamic time warping. The first one is monotonicity. So what does it say? So if you have two sequences which are laid out like this, that means here it's the ith uh, index I and here is the index j. And if you have two sequences p and q, so let me take this as p and let me take this as q. So here it will be p1, p2 up to pn, and here it will be q1, q2 to qm. So once we have this specific matrix, so each of this p and q are what? These are the feature vectors. Feature vectors for ith time instance. In case of pi, ith time for p or jth time for q. Okay, so once we have this, we construct a specific matrix, and those specific matrix should have some nice properties. That the first one is monotonicity. Monotonicity means that every point on the specific monotonicity ensures that every point on this uh, rather every feature vector on P maps uniquely to every feature vector on Q, and they are continuous. They are not randomly placed because this can also be monotonic, but this is randomly placed. So since it's a time series data, you need to make sure that they are continuous as well. So things like this help monotonicity. And the next property is continuity. So I'll write these properties. This is monotonicity. The next property is continuity. That means I cannot have breaks in between. So this is not continuous. You should make sure that the curves that you're getting that matches the vectors from pth sequence to the qth sequence is continuous. And once that is done, you also have to ensure a few other things that the boundary conditions are satisfied. That means every sequence should start from here and to here. So once you have these conditions, it makes sure that all parts of the sequence are mapped to all parts of the sequence in the other sequence. Okay. So and after that you have a warping window as well because you can get weird mapping sometimes like this. You can trace this kind of path, but this path is of course not so useful. It doesn't really give us information about how the sequences match because what it means is all values of p's are initially being mapped to q1 and then all values of q's are mapped to pn, which is not informative enough. So we want more variability. So we make sure that we have some thresholds like this and our sequences are mapped within this region. That's what it means to be having a condition for warping window. And the last one is the slope constraint. So the slope constraint also makes sure that if your slopes are like this, if it's flat, then it means that a particular feature vector is mapped to many feature vectors there. That means a small part of the feature vectors are getting mapped to a larger part of the feature vectors, which we don't really want if we want it to be expressive enough. So that's why we also have this condition of slope. Okay. And then based on this, there are a few different algorithms that were given in the class. One of the algorithms that we'll be discussing as we do the questions. Okay. So we move on to the next topic, which was discussed hidden Markov models. So can anyone tell what is hidden Markov model? Anyone? Okay. So what is the main idea? Here also we are trying to do gesture recognition. But for gesture recognition, there might be uh, so what we actually do is we get some features from different time instances, and then based on that, we would like to recognize whether those features correspond to a specific gesture or not. So that's the core idea. And hidden Markov model, well, that's a general probabilistic model. What it says is any these set of feature vectors map to an output vector through some intermediate states, and those intermediate states are uh, is what decides how the output looks like. So if you have an input which is a set of feature vectors, they might give you some intermediate states in some form, which is probabilistic in nature. So if you give the same set of intermediate states, it is not necessarily the case that you will get the same output always. So there could be some probabilistic nature in that system, which is captured by the hidden Markov model. And how many number of hidden states are there? That depends on the nature and the complexity of the application. And in this specific case, if simple gestures like writing one or writing five, which does not generally lead to taking your hand out of the paper when you write it. So they are relatively simple. But if you want to write something like four, or yeah, four is one example where if you write it in this manner, you have to take your hand out of the paper and then do it. Or maybe seven, some people write seven like this, some people write seven like this. So depends on how you write it. This makes them really complicated. And there might be many states which map to the same output. Okay. So these things, this sort of randomness is captured using the hidden states and the hidden Markov model. So that's the core idea. So the core idea, as I said, I'll just write it pictorially. So this is input feature vector, which you would have extracted from different sources. Once you have that, so there is a hidden Markov model where there are a number of states. You can just label them, and then they will have interconnections of how they will go forward or backward, and the values of these states. So if there are states S1, S2, S3, and S4, the values of the states gives what? These determine the output. Well, the states can be discrete, maybe binary, zero or one, or they can be real valued vectors. They can take any real valued elements here. So the easiest way to do it is with one of the states are active at any point of time. And if one of the state is active, that means one of the gesture has been recognized. That's what is generally used in case of gesture recognition. That means S1 represents one specific gesture, S2 represents another gesture, and so on and so forth. So if you have too many combination of gestures, then you will have many hidden states there. And whichever state is switched on, that means if you take a binary vector, if this state is switched on, then you consider this to be a uh, final gesture. Other gestures are not detected from the given input. Okay. So based on this, the most important thing that I said is this is a probabilistic model. That means whatever arrows that I'm drawing will have a probability value assigned to it. That means going from state one to state two, there will be there is only some probability that it will travel from here to there. I mean, you can move from state one to state two, or there's some other probability that you can go from state one to state three. And of course, as you know, the sum of all the probabilities going out should be one, because you cannot have probabilities greater than one. And one more probability is there is the observation symbol probability, which gives us the probability of observation from for the present state of model. So whatever state, if you are in state S1, what is the observation that you will get if you are in state one? That is also a probability there, and it's not just changing of the states. So there are two types of probability distributions being used, and the initial state distribution. So initial state distribution, you can say that if someone starts to write like this, probably that person is trying to write a one. Well, so one might represent this state S1, but someone then can just change it like this and write like this. So it might have some other state S5. So initial state also determines how quickly you are able to get to the correct output. So there are three sorts of probability distributions one can that one needs to model before they start working with hidden markov model. Okay, so there are a few other things as well that were discussed in that specific lecture. We can move on to the next one, which is the background modeling and motion estimation. What do you think is background in images? Anyone? Background. So whatever the objects that are not of our interest, we generally call it as background. The objects could be walls or some scene which contains the sky and maybe the horizon and some forest area or mountains, things like that. So they are generally not of our interest. Whatever the object is at the front of the camera, they are of our interest, and that is and the and those objects are called as foreground. Okay, so that is for a single image. But when you have a video, you can say that whatever uh, objects which are moving, they are the foreground, and whatever objects which are not moving, they are generally not of our interest. So we call them as background in case of videos, and that's how is it is used in the current discussion of the lecture that you can detect a moving car or people moving in the scene. For that, you can use this. First, you need to segment out the foreground from the background, and once you segment out the foreground from the background, there can be different applications. Like you want to track the specific object, how it is moving, and maybe you have too much information. Like instead of a single camera, you might want to use multiple cameras. Using multiple cameras gives you multiple views, and if you have particular correspondences between the two views, you can get you can be more precise of the trajectory that object is moving. Of course, but as soon as you add more data to your input system, the computational complexity will increase to a good extent. So you need to take care of a balance, whether you want preciseness or you want it to be real time. Because real time systems may not be that precise, but if you increase too many things, you can get precise answers. That means precise tracking of the object, but you may not really do it in real time. And of course, there are other problems to it, which is if the object moves abruptly, that means object can move in some weird manner, probably because that was not captured by the camera, or maybe there was some occlusion there due to which we were not able to track the object. So in that sense, in those cases, the objects can move abruptly, which makes it even harder to solve for the path in which the object is tracking. And there are other problems which are discussed, like if the objects cross each other, that means they are merging in a specific imaging camera. But maybe if you have multiple cameras, your problem is solved because they might not merge in both the views if the cameras are placed properly. So there are a few things that were discussed in the object tracking as well. One is simple motion based tracking. What you do is you take the background from two consecutive images of the video sequence and then different take the difference. Whatever the difference, if the difference is greater than lambda, that means some threshold. What it gives you is the foreground of the object, foreground of the image. The other part is the background where there is no difference. Of course, you have to take care of the noise. That's why you keep a threshold instead of keeping absolute zero. Um, so this method is called as background subtraction. The next method is called as Uh, the next method uses a Gaussian model, so they call it a single Gaussian model. So there you assume that every pixel in the background follows a single and separate Gaussian distribution. That means every background pixel, if I have some image like this looks like a tree, which is fine, but if these are the background pixels, every background pixel will have a distribution with mean and variance. I'm writing it ij for the pixel I comma j. And for every I comma j, you would like to update these parameters mu and sigma. And if you think that uh, your specific, so for any given part of the image, if the intensity is I, if it crosses, if the difference from the mean is greater than some constant times the standard deviation, then you classify it as foreground, else background. If it's within the limits, then you call it as background. Well, that part of the pixel is well, that pixel is the background of the image. That's what I'm trying to say. And then you can also generalize it using mixture of Gaussians, since you may not know what specific distribution this follows. So the mixture of Gaussians can try to model the background in a better sense than using a single Gaussian. And one of the most famous technique, which is the Lucas-Kennedy technique, it is still used in practical scenarios. So there you try to get optical flow from two different images. Once you have an optical flow, what does optical flow means? That for every pixel, so for every pixel I comma j, what you have is you have a vector defined uv. Okay, so that vector gives you in which direction that pixel moved between the two frames. So if I have frame one and if I have another frame two, so if I add for this specific pixel, if it shows uv at I comma j, if you add this specific value u comma v, wherever you land in the next image, that specific pixel will correspond to the original pixel here in the frame one. That's what you mean by optical flow. That means I nu, j nu can be given using I j of the current plus the optic flow value. This is the optical flow. Optical flow. So this is the core idea of optic flow, that if you have the displacement vector for each of the pixels, then you can easily track how the specific pixels are moving. And that's why it's very commonly used, not just here in object recognition, but in other places. For instance, if a robot is moving in an unknown environment, it might want to track a few things, how it is moving with every frame. Then this Lucas Kennedy technique is still used in practical systems. Okay, so what it suggests is that you can, if you have two images, you can get some idea of how the motion of the object happened. But there are instances that was given in the class where optical flow, if there is an optical flow, that doesn't mean that there has to be a motion of the object. So, for instance, if an object is like a mirror sphere, uh, if this is a mirror sphere, and if that object rotates with the specific axis, and if you have some lighting source like this, only this part is shiny, other parts are non-shiny. So even if it rotates, and if you try to capture this whole thing with a camera, you try to capture this part as with the camera, you cannot distinguish between the two images. So there may not be optical flow, but there is actually a motion. The motion exists for the object. And another example that's given is if you keep the object constant, but now if you rotate, uh, keep the object constant, but now if you move the light source from here to there, you might see that your shiny part of the object moved from one place to the other, but what actually moved is the light source. Probably because once you would have clicked it in the morning, the other time you would have clicked it in the evening, but there is no actual motion of the object. The motion comes because of the lighting. So there's optical flow there, but there's no actual motion of the object. So both the things are not the same, but in most general conditions, if you think that your lighting source is fixed, like inside a room, and if your object is not symmetric like this, and it has some other specific features, for instance, even if it's symmetric, it might have some texture which can be recognized easily, which is generally the case in the rooms that there will be some part of the room which can be recognized uniquely. Then you can make use of the optic flow to track the object. Okay. So based on the constancy condition, what whatever I discussed here. So instead of I comma j, I can write it the pixel values as x and y. So if I move by u in x direction, y by v in y direction, and if I move by delta t in the time, this should be the same as the previous one. This is what the optic flow says. And if you try to take Taylor series approximation of this, what you end up getting is this thing is equals to e of xyt plus change in x times the gradient with respect to x, change in y times the gradient with respect to y, plus change in time, gradient with respect to time. So this should be same as the right hand side, which is the original intensity value that we saw. What this gives us is the gradient vector with this variable vector should be zero. This dot product should be zero. So this is completely fine until you see that now in this expression is completely fine. There is no problem with the Taylor series approximation. But then there was a thing discussed in the class that what you do is you divide by delta t and take the limit of delta t to be zero. That means it turns out to be like this. So this is at delta t tending to zero. It looks like this, which is still fine. But in practical applications, what this delta d should be, you don't know previously because your frame rate is generally 25 frames per second, and whether that delta t is enough for the scene that you're capturing or not is something that we don't know. Because if the motion is small, maybe even frame rate of 10 frames per second is good enough. But in case when the motion is very high, it could be the case that you need higher frame rate like 100 frames per second. And that's why there's a very good optical illusion video that has been viral in social media for a long time. That is, helicopter is moving without its blade being actually moved in the space. But the point is, its blade, the frame rate of the camera is same as that of the frame rate of the blades. That's why ultimately what you see is that the blades are not moving in the helicopter, but it's still flying. Okay, so this is what was given about the optical flow in the lectures. And the last topic that was given is the object tracking. So, what do you think is object tracking? Okay, so whatever we discussed till now, all these things are also using object for object tracking. So, for in object tracking, one specific thing that we need to deal with is once the object tries to move with specific illumination, it could be the case that the shadows are also present in the image, and once the shadows are present in the image, the shadows will also be moving. So one of the ways that can be used to remove the shadow is, as discussed in the class, the shadow changes greatly in terms of intensity, but the chromaticity does not change. So based on that, you can, if you find a part of the image which was moved, but its chromaticity, that means the colors are not changing much. Maybe the intensities are changing, but the color is not exactly changing. Then you can remove the shadow part. It is based on the decomposition that we discussed in the early lectures. That is, the image can be decomposed into intensity part and chromaticity, illumination part and the chromaticity part. Okay. So the illumination part changes, which is the intensity here, but the chromaticity part won't change. That's how you can remove the shadow. And for object classification, one of the this is just for object tracking. Then comes the object classification. What you can do is one easy way to do is just use simple maths. That for specific kind of shapes, you will have a specific. If you define parameter like dispersedness, then which is defined as perimeter square upon area. So it is the perimeter of the object that you see, and versus take the square of it divided by the area of the object. So in general, it's generally found that this specific ratio is constant, not constant. It lies in specific range for different kinds of object. For the paper that used it, uh, this is you can have different one for you can have different ratios for people, you can have different ratios for cars, and so on and so forth. That's why you can use this specific parameter to decide whether there are objects or not, objects there or not, or rather which kind of objects there are present in the image. And the other one is the silhouette based method, which was not discussed in the class in depth. The one way to do is the object tracking, or is to make a model of the object. For instance, if you want to track humans, you have humans probably having this kind of structure where these are the legs, this is the torso, this is the head, and this might be the hand. Once you have this, you can make sure that you can track this model. Once you track this model, it is possible to track the whole human, for instance, among the frames. Okay. So other ones is the feature-based tracking, that different parts of the body have different features. For instance, if some part of the body has different colors, then you can use that as a feature and then try to track those features. But that might not be robust because the background can also be of similar color. So there You can extract shift features, for instance, and then try tracking different parts like eyes or nose among the frames. And then there is another thing called as blob matching. What is blob matching? Which is also a way to track images or track objects. The first is you get specific blobs. The first part is to get blobs in the current image. And once you have blobs in the current image, match it with the objects in the previous image. Once you have matched it with the object in the previous image, so there will be this is one way matching. Now, to make it robust, what you need to do is whatever the matched object that you got, matched object uh, in step two will be matched, will be used to match all the blobs in the current image. If you see that in both the sides, that means matching blobs gives you a specific object, and the specific objects gives you back the same blob. That means you have been able to track that object. Else you have failed to track the object. And it's not necessarily that the matching is good enough. Again, you have to do a good amount of pre-processing to make sure that you are robust to changes in illumination conditions and other things. Okay. And one more algorithm that was discussed just for this object tracking is the mean shift algorithm. Well, that is very useful in case of segmentation. So once you segment your images based on, for instance, if your images have different, if you have an object like this, probably it's a donut. So this will have one color and the other parts will have other color. So what you can do is you can uh, take the feature space where these colors of the object will be mapped here and the background colors will be mapped here. So once you have all the mappings here, you just take a specific pixel here, and then that specific pixel might correspond in this part of the feature space. What you do is now you take a region. Once you take a region, you move this region based on the uh, centroid of the mass present in this region. Once you have centroid of the mass present in this region, you can move it, move the centroid to the next position. Once you have centroid to the next position, you can just shift it, shift the whole. You can move the centroid here and then take another region. And based on that, all these points in this region will converge to the same point. So that means every point here will converge onto the same point. So that's how you can easily segment this part of image. So once you're able to segment, that means you detected an object. So once you detect an object, then you can easily track it based on the other methods that we discussed. And the last topic that was discussed in the course was about recursive filters. So these are all based on the state space model. That means the state determines where your current object is. It gives you the trajectory, or the space defines where the current object is. The state defines how the object will move. And yeah, that's why it's called as the state space model. So in the specific case of the Markov random process that was discussed in the class, there is a state equation and there is an observation equation. So the state equation depends on the previous state and the current noise or the input that was given to the system, which changes the state, which is given like this. State equation is given like this. Xk is a function of the previous state and the current input. And the observation equation is given as this. Uh, this specific equation where this is the observation, this is the current state, and this is the noise associated with the observation. So these two equations are generally called as the state space models, and all the Bayes filter and its derivatives. And its derivatives like Kalman filter or extended Kalman filters, all are derived using the state space model. Okay, and of course now these things comes with a lot of assumptions there that they are Markov models. Well, the Bayes filter doesn't come with Markov model, but the Kalman filter assumes that it's a Markov model. That means the current state depends only on the previous state and some observation vector, and you don't need to know all the previous states in time. And particle filter also tries to get the same thing, but here the problem is uh, for Kalman filter you assume Gaussian world. That means everything has Gaussian distribution, and they are linear models. So which makes it impractical to use. Extended Kalman filter still works with Gaussian models, but they work with nonlinear models. And this was the filter which was used to track the rocket in the Apollo space missions, and that's why the first moon landing occurred. Okay, but for particle filters, what happens is you have you again have all the same things, but no Gaussian assumption is there. No Gaussian assumption exists. So that's what makes it more powerful than the Kalman filter. So what's the core idea of particle filter? That here you are trying to model the probability distribution function. That's why you don't assume any kind of distribution, but you try to model the probability distribution function. It is similar in spirit that of non-parametric uh, method to get the distribution. Okay, that's all there is to it from the lectures part. Now we'll move on to the questions for the week.
Hello.
Yes.
Can you explain how to find a convolution matrix using the image matrix and the filter? So, like we had this one question where the 28 by 28 image size was given and 7 by 7 kernel size was given. It is not, I guess, related to the whatever you taught today, but it is related to the convolutional neural network.
Yeah,
Like,
we'll do that question.
okay.
Yeah. So, so this specific question, this is the first question that we have from the assignment. So you need to get the best dynamic time warping alignment of the path I comma j for the two sequences. Was anyone able to solve this question?
No, actually, I was not able to solve it.
Okay. Well, the question is incomplete if you see. We don't know what the sequences are. There should be two sequences given to us, which is P and Q. Once you have the sequence, we know the procedure on how to proceed with it. But since we don't have any sequence there, we are not sure of which answer to choose. So just to give you the concept, I'll just assume that P will be PIs, because I is 1 to 5 in this case. So I'll take this as P and I'll take this as Q. The feature vectors, what I will take for solving this is directly the numbers that you have, 1, 2, 3, 4, 5. And for Q, again, I'll take the same feature vectors. This is just for understanding the concept, but the feature vectors can be different from the index. I'm taking the index number as the feature value, but in practice, of course, they are different. So what each of these defines, as we discussed, it depends, defines the feature vector for each of the time instant. Since these are all time series data, so this defines the features at each time instant. Okay, so what we can do now? So the first thing that we need to do is construct a Dij matrix, which is the distance matrix. How does the distance matrix look? So that Dij should be the absolute difference between Pi and Qj. Okay. So in our specific case, I'll just rewrite the matrix. Here one, here there are 5 feature vectors, and here there are 8 feature vectors. Okay, now given this matrix, what we need to do? We'll just take the absolute differences of the features. So the feature at 1 is 1, Q here, and P here. Since that's how I defined the features here. So what you'll get? So here it will be 1 minus 1. Absolute differences. 1 minus 1 is 0. 1 minus 2 is minus 1, but we need to take the absolute difference. What we get is 1. The next is 3 minus 1, or 1 minus 3, it is 2. 1 minus 4 is 3. 1 minus 5 is 4 in absolute sense. So what you see is that you will have zeros along this diagonal, and the off diagonal elements will look like this. Again, every number will be copied like this in a diagonal fashion. So this is why am I getting this pattern is because I've chosen the index number to be same as that of the feature. But in exam, that will of course not be the case. You will have specific values of Pi and specific values of Qj, and you have to take their absolute differences. So once we have this matrix, this is the distance matrix. Okay. All right. So once we have this, what we need to do? So we'll now construct another matrix based on the distance matrix to get all possible paths. matrix to get all possible paths. Yeah, what we have here is this specific matrix again, but now we have to process this matrix. This is 0 here, the first and the lower diagonal part will always be 0, the lower left part. Once we have this, what we need to check is, now we'll start constructing this matrix. So here we have 0 value plus, we'll add the next value here. So 0 plus 1 gives me 1, and here the current value is 1. 1 plus 2 for the next value is 2. This, that gives me 3. Now I have the current value 3 here, 3 plus 3, which is the next value. So that gives me 6, and 6 plus 4, that gives me 10. So that's how you get the first row. First row, how to get it? Take the previous value and add it to the current value in from Dij matrix. So once you have that, you can fill this matrix here like this. What you need to do here in terms of column, again you need to do the same. So what you get is 0 here, and then the next value is 1. 0 plus 1 gives you 1. So this pattern continues here. 1, 3, 6, 10. Once you reach here, 10 plus 5 gives you 15, and 15 plus 6 gives you 21. 21 plus 7 will give you 28. So again, the first column, take previous value in column, and then add the current value from Dij matrix. Same thing, but you do it in column. So once you have this, what is the next thing that you would like to get? Uh, this matrix, this element. So for this element, we take the minimum of these three, which is one to the left, one to the bottom, and one to the diagonal. And we take minimum of these. So minimum of these three is 0. Once you have 0, you add the current value to it, which is 0 from the Dij matrix. 0 plus 0 gives me 0. So now I'll fill row wise always. I don't have to think about columns. So what you will do is, now you check for this specific element. How do you check for this specific element? Yeah, the current value is 1, and now you check for the three elements that are here, which is like this. Minimum of these three is also 0. 0 plus 1 gives you 1. Okay, so you can just try filling again here. So minimum of these three is 1. 1 plus 2 gives you 3. So if you start filling the matrix like this, again you tend to get a nice pattern. So all of these diagonals will have the same value. Well, again, I'll mention that it's just because the index value is same that as a feature vector. Once you don't have that, specific pattern, you will not get this kind of matrix. So this is how you get the matrix. So once you have the matrix, what you need to do? So this is the final step. Final step is you start from the top right corner, choose this one, and then move to the value which has the lowest number in the next three neighbors. Three neighbors, the three neighbors from the left side, like the way I choose here. So from here, I'll move here because 3 is the lowest. And again, if you check all these three neighbors, you see that 1 is the lowest value. So I move from 3 to 1. Again, from 1, I'll move 0. Once you're here to 0, you check the three neighbors again. What you see is this 0 is now the smallest value, and this is how it continues. So this is the final answer. What your final answer should look like is 1 comma 1, then 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, because all these are zeros, which are minimum, and then once you go here, then 6 comma 5, 7 comma 5, and 8 comma 5. So yes, this is the final answer if I take the specific feature values for the indexes, but if you have some other feature values, you will get the different answer. So the idea here, so what you are able to observe here is that there are too many things here which are mapped to the same thing in the sequence Q. So from sequence P, there are many things which are mapped to the same sequence Q. So what we generally try to do is we try to uh, get some variation with the five properties that we discussed during the lecture. And that helps us to get a more better mapping from P to Q than such skewed mapping. Okay, so is the method clear for this question? Any doubts? So I'll just revise that. Once you have this feature vectors given, you just create a matrix with the number of feature vectors in each dimension, and you check the distance between the two feature vectors. Once you know the distance between the two feature vectors for each individual element, you just fill this matrix. Once you have filled the matrix, you can now create another matrix where the lowermost corner is just the copy of this Dij matrix. This is the Dij matrix. Once you have the once you have the lowermost corner, the next element in the row is just adding the previous element in this new matrix plus the element from the Dij matrix. So 0 plus 1 is 1, 1 plus 2 will give you 3, 3 plus 3 will give you 6, and 6 plus 4 gives you 10. This is how it works. And again, you do the same thing along the column, move along the column. Once you have the smallest row and smallest column filled, you now check for the three neighbors for each of these elements. That means you're considering both row and column and this type. And based on the three neighbors, whichever is the lowest, you pick that and then add with the current element in the Dij matrix. Once you do this, you keep on doing this iteratively for all the elements here. Once you get this final matrix. From this final matrix, what you need to do is from the top right corner, track whatever is the smallest element in the left three neighbors. Once you choose the minimum of the left three neighbors, just move to the next neighbor. And again, choose the minimum and move to the next neighbor. And that's how you track this whole sequence. Once you have this whole sequence, you just write it down from bottom to top. And this is how you get the uh, answer for the dynamic time warping. Okay, then we will move on to the next question.
Sir, I have
Yeah,
a doubt.
yeah,
Uh, The answer we are getting is not matching with the assignment answer.
Uh, what answer did you get, by the way?
Here
What
there
I
is a
wrote,
no.
whatever I wrote is will of course not be the same as that of assignment because they have not given P and Q values. So are they displayed in your assignments? The specific values of P and Q, what are the sequence values? These are the feature vectors that you need to get the distance matrix. Do you have those values by any chance?
No, sir. They haven't mentioned what is the P and Q.
Yeah, so that's why I just cooked up some values here. And I just took the index value as the feature value and got this matrix. But in the exam, you will be given a P and Q values. Based on that, you'll just follow the procedure that I told. That will give you the right answer. Okay. Okay. So yeah, this is the next question. The particle filter, which of the following statements are false? Okay. Particle filter can make Markov assumption about the system dynamics. What do you think? Is it true or false? What is particle filter? As I said, it was based on state space model and it does not assume that all the probability distributions are Gaussian. It does not assume anything about the probability distribution. And so it tries to estimate the distribution function using uh, the particles that you saw in the class, the size of particles and the position of the particle. So the particle filter, can it make Markov assumption? Yes, it makes Markov assumption from the state space model. Markov assumption, I'll just write it here. Particle filter makes Markov assumption from state space model. So it is true. What about the next one? Kalman filter can update results in a Gaussian belief state propagation. Well, belief state is nothing but the probability distributions that we have seen. Yeah, so everything should be Gaussian there. So Kalman filter can only be used under such conditions. So Kalman filter assumes all distributions are Gaussian. So this is also true. Okay. What about the next one? Kalman filter can make use of an iterative process in order to produce its estimations. Is it true or false? Anyone? This was given in the slides as well. So there are two steps for Kalman filtering, right? One is the prediction step, and another is the update step. Prediction step is whatever input that you are given. Based on that, what the next position of the object should be. That will give you the prediction step. Update step is whatever observation that you got. Based on that, what is the position of the object? That's what is given by the update step. So Kalman filter iteratively uses prediction step and update step. So yes, it's an iterative process, and based on that, it is able to refine the estimates. So this is also true. I guess the last one should be false, but anyways, we'll check it. Particle filters can be used to solve Gaussian noise problems only. No. That is false because particle filter has no assumptions on the distribution, on the probability distribution of the state space model. Okay, so the last one is false, and that should be the answer. Is this question clear? Okay, I guess it's clear. Then we can move on to the next question. So the next question is we can measure components of optical flow in which direction? So what do you think? In the tangential direction to the intensity gradient, in the perpendicular direction to the intensity gradient, in the direction of the intensity gradient? None of this. Anyone? Okay, I'll take a specific example that will answer all these questions for you. So assume that this is the lens that you are viewing and you cannot see anything beyond the lens. And this is how the image looks like. So there are lines in the specific direction. Okay. Once you have lines in the specific direction, what do you think? If I move in this direction, can you get the difference? Your object has lines like this. That's all. So if I move in this direction, can you see any difference in the optical flow? That means, can you see any difference in the image through this lens?
No.
Yeah, you can't see the difference because you will still be tracing along the lines. So whatever image you take, even if you move along this direction, it gives you the same image. So what this says is you cannot detect in this direction. Cannot detect in this direction. And what about the other direction that we have? Maybe this direction because this is perpendicular to this direction. If I move in this direction, can I detect the changes?
Yes, sir.
Yeah. So can detect changes when moving in. So what does this mean? So if this is the image, for instance, and these are the lines, how is the gradient? Since every question is related to gradient, so how will the gradient be? Gradient is what? Gradient magnitude. Uh, so magnitude, gradient magnitude is, I'll write it as mg, which is what? Gradient in x direction and gradient in y direction. This is one of the way you can measure gradient magnitude, right? Which is the del I by del x whole square plus del I by del y whole square, and then take the square root of this summation. So what do you think about the gradient magnitude? This is dependent on magnitude, and the direction theta is given as del I by del y upon del I by del x, right? Tan inverse of this quantity. Change in y by change in x. That's how you get the direction. And what this question demands is we need to get an idea of where can we measure the optical flow components. So what this now converts here is, well, what is the gradient direction in this specific image? Can anyone tell that? How will the gradient direction look like? Looks like this. Yes, agreed. Okay. No response means I'll assume. Okay, so once we have this, so this is the gradient direction that we have. Yeah, this is the gradient direction. And what we see is that you can detect changes when your lens is moving in this direction, but you cannot detect changes when your lens is moving in the perpendicular direction. So in the direction of intensity gradient, you can detect changes. This is right. Okay. In the direction perpendicular to intensity gradient, that means in this direction, you cannot measure the intensity gradient. What about the tangential to the intensity gradient? Any idea what is tangential to intensity gradient? Is gradient a curve? You can take tangents only for the curve, right? Gradient is not a curve. It's a field. Since it's a field, you cannot take tangent to gradient. So that means the first option is anyways wrong. You cannot take tangent to the gradient, tangent to the intensity gradient. So your final answer is we can measure components only in the direction of intensity gradients. Is this question fine?
Yes, sir.
Okay, great. Then we'll move on to question. So the next question is on hidden Markov models. Back again, not back again, but the only question on hidden Markov. Okay, so this is a very commonly asked question in interviews as well. If you interview for any of this artificial intelligence or machine learning kind of uh, degrees, then it's a commonly asked question, especially at a graduate level. Okay, so consider the following state transition diagram with three states. So there are three states given to you, which is sunny, foggy, and rainy states of the weather, and the state transition probabilities are mentioned. That means if it's sunny, the probability that the next day it will be sunny is 0.8, probability that the next day it will be foggy is 0.15, and it will rain on the next day is 0.05. Can you see anything specific? It's a probability that some things should sum up to one, right? What are those things that you see are summing up to one? Anyone? Okay, all the outgoing edges sum up to one. Can you see that? 0.8, 0.15, 0.05. It's 1. So these three edges are coming up to
Yes,
1.
sir.
Yeah. What about this? 0.5, 0.3, 0.2. This should sum up to 1. And this one is 0.6, 0.2, and zero point 0.2. You can clearly see that all these things are summing up to 1. That's why there is a probability distribution, underlying probability distribution for the transition, as I said during the discussion of the lectures. Okay. So now suppose that you are locked in a room for several days, unfortunately, that we don't know. But anyways, if you're locked and you're asked about the weather outside, you have to predict what would be the evidence, predict what's the weather there. And the only piece of evidence that you have is whether your caretaker is carrying an umbrella or not. So good that at least you have a caretaker. And if that caretaker carries an umbrella, uh, in specific weather conditions is zero point 0.1 for when it's sunny, zero point 0.8 when it's rainy, and zero point 0.3 when it's foggy. Okay. So suppose you do not know whether the weather, you do not know about the weather when you were locked, and the caretaker comes with an umbrella, without an umbrella for 3 consecutive days. So what this gives us, this is giving us observations, and this is the probability distribution whether uh, that person carries an umbrella or not in the different conditions. And the this diagram gives you the probability distribution of how the transition happens from one state to the other. Okay, so now calculate the likelihood of the weather on these 3 days to have been. That is, the first day is foggy, the second day is foggy, and the third day is sunny. Since we don't know that the weather on the first day how it is, so you can assume that all the weather situations are equiprobable. So use the concept of hidden Markov model. So was anyone able to solve this question? Looks complicated, but it's actually not that complicated. How to proceed with this? Anyone? First, we need to formalize what we want to do. So, what are the things that we want? What we need to want is probability that the first day Q1 is foggy. I'll write F for foggy. Foggy equals F. Uh, yeah, we have three distinct letters, so I guess we can directly use it. Sunny is S and rainy is R. So probability that the first day is foggy, second day is foggy, and third day is sunny. That's all we want? Yes, that's what is written. Calculate the likelihood of this three weather condition on these 3 consecutive days. Okay, but then what? Then what? Then you have to see that what data you have. So the data is that the caretaker has come without an umbrella for 3 consecutive days, for these 3 consecutive days. So given that, so X be the random variable, which is what? Either 0 or 1. 0 means no umbrella, and 1 means umbrella. Okay. So if you have taken any probability or statistics course, then the course instructor always expects you to write these things in detail before actually solving the question. Okay. So X is the random variable, and 1, 2, 3 is for the specific day. The subscript is for the specific day. Subscript denotes the day. Okay. So the first all 3 days, that person did not carry an umbrella. You will write it in order because we'll use that soon enough. So this is what you want. This is how to formalize this whole statement in maths. Okay. So what is this? This is the posterior probability. Why is it posterior? Because you want to see whether that where how the weather looked like on those days given the observations. So when you're given the observations, it is always posterior. You want to estimate this given observations. Well, here we are not estimating. You want to see whether this specific condition happened or not given these observations. That's why it is a posterior probability. In prior probability, you will check what is the likelihood of this observation given some specific weather condition. Okay, so that will be the opposite. So using Bayes rule, what can I write? Probability that x1 is 0, x2 is 0, x3 is 0, given this q1 is f, q2 is f, and q3 is s into the prior probability. Prior is what is the probability that this three consecutive days happen. So what this is the likelihood part, and this is the prior part. Okay. Okay. So till now we have not used anything about Markov random field. This is just Bayes rule that I have applied. Okay. So I'm breaking it down for you because it will be easier to understand here. If I directly write the Markov random field, then it may not look that obvious to how to proceed with this question. Okay. So what is this? X1 is 0 means you have observed something. So that observation should depend only on the current day, right? And not on the future days or the past days. Yes.
Yes, sir.
So what you make here is the independence assumption. X1 equals to 0 given Q1 equals to F. What independence assumption is that? What is the independence assumption? That that person carries an umbrella based only on the present day condition, weather condition, and not on past or previous day. Here it will be X2. This is coming from independence assumption that caretaker carries umbrella based on current day weather condition. Okay. So and now you have other terms as well. What is this term? This is like the joint probability that when two continuous foggy days happens with the third day being a sunny day. Okay. So what I can write probability that Q1 equals to F into probability that Q2 equals to F, Q3 equals to S, given Q1 equals to F. This is coming from Bayes rule. Yes. Oh, this is not even coming from Bayes rule. This is the simple. If you know this, probability of A given B is probability of AB upon probability of B. That's all I'm using. Yes, this is coming from this expression. Everyone agrees? I'm just conditioning it on Q1. Okay, fine. So I'll just rewrite that first part, probability that x1 equals to 0 given q1 equals f. Same thing here for the second day. And I'll also write it for the third day. is sunny, and then I am writing this expression again. This is the prior probability that I have. And what is this? I can break this again based on this equation. Probability that Q3 equals S given Q2 equals F into Q1 and Q1 is F into probability that Q2 is F given Q1 is also F. That's how you break this one, right? So keep this as constant as given, and then take these two and apply this formula here. So Q2 Q3 will come like Q3 by Q2 into Q2. That's all I did. Q3 by Q2 into Q2, and this thing is constant there. So again, I just place the values, and the last line will be the last assumption, which is what? Is the Markovian assumption. This is the Markovian assumption. So the current day weather will depend only on the previous day and not any other day. That's all you need, right? This is current day weather depends only on previous day weather. So now what you have to do is just copy paste the values. Okay. The probability that x1 is 0 given that q1 is f means probability that the person does not carry umbrella if it's a foggy day. What is that probability? It is 0.3. Yes, am I doing right? Okay. Yeah. So what's given here is that probably that caretaker takes umbrella if it's foggy is 0.3. So here he's not taking umbrella. That's why x1 is 0. That means you should take 1 minus 0.3, which is zero point 0.7. So in foggy case, its probability is 0.7 that he won't carry the umbrella. Again, the same case for the next day. And the last one is he doesn't carry umbrella when it is sunny. So for sunny, it's zero point 0.1. That means uh, not carrying umbrella will be 0.9. Okay. And what about this? Probability that it's a foggy day, the first day is foggy. We are given that they are equiprobable because we don't know how the weather was on first day. So how many states are there? Three states. So what we do is it's 1/3 since it's equiprobable. This part is 1/3. Okay. And the next part, probability that the next day is sunny, given that the previous day is foggy, is what? You have to transit from foggy to sunny. Yes. So according to this diagram, what is from foggy to sunny? It is
Point
point
two.
2. Yeah. This. And what is the probability that you are transiting from foggy to foggy? Uh, that is the self loop that you see. It's zero point 0.5. Okay. So this is your final answer, and if you just compute it, I guess it turns out to be. Is this clear with everyone? Any doubts on this question? So what I have done is I have just first written the base rule here. This is the posterior probability since we are conditioning on the observation and we want to check whether a specific condition of the weather happened or not. So it's a posterior probability. Then I converted it into likelihood and prior. Likelihood, there is an independence assumption that the umbrella, whether it's taken or not, depends only on the current weather condition and not on any other day's weather condition. And I just applied the basic conditional probability formula for the second part here on the prior. I reapplied that on the prior, and what we now get is all the expressions is something that we know. After making this Markovian assumption that the current day weather depends only on the previous day and not on any other day. So once we have this whole thing, we just replace the values, specific values, and we get the final answer. Okay. Fine, then we'll move on to the next question. Okay, which of the following statements is about the clustering is or are true? Okay. K means is no explicit estimation of probability density function. Is it true or false? What is K means clustering? You get the centroids of different clusters, right? That's the whole idea. It doesn't assume any probability distribution, underlying probability distribution. Yes. And so whatever the cluster centers are, they are representative of the actual probability distribution of the data. So it is not an explicit estimation, but we are implicitly representing it using the centroid. So it is true. Okay. Centroids, not explicit. Okay. We move on to the next part. Mixture of Gaussian is parametric estimation of probability density function. Is it true? Anyone? Yes, it's true, right? How many what you have k number of Gaussians in mixture of Gaussians, and all those k Gaussians will have what? Mean and variances. So they are all parameters that are needed to be estimated. So it's a mixture of Gaussian. So mixture of Gaussian is a parametric estimation of the PDF. So it's true. What about mean shift? Mean shift algorithm is a non-parametric estimation of probability density function. Yes or no? Yes, you try to shift the means, right? As I told, if you have different data points and then you start from a given point, you select the region around that point, and if the region has the centroid here, the center of the mass within this region is here, then you move it here, and then you create a new region and then keep on moving. So if there are two sets point clusters here like this, that means if you initialize nearby this cluster, it will converge to this cluster, else it will converge to this cluster. So these are all non-parametric estimation. You did not assume the form of probability density functions. That means all of them are correct. So the final answer is this. Okay. Any doubts? Okay, then we can move on to the next question. Too many question answers, uh, theoretical questions today. The condition of dynamic time warping, which guarantees that the alignment does not omit important features, is what? Okay. So we'll go through one by one. What does monotonicity do? Hmm? Monotonicity ensures that there is a one-to-one mapping. So when you created that matrix, you don't want things like this because one feature vector here is mapping to multiple feature vectors here. So this is not desirable. So one-to-one mapping is required for monotonicity. Continuity means, see, you can have something like this, but here you are missing some feature vectors. So continuity avoids missing feature vectors. Yes. So this is, well, that's what it says the question. So it does not omit the important feature vectors. So this should be the right answer. What is the boundary condition? Anyone? Boundary condition makes sure that you're starting from this point and ending to this point, which gives you, which ensures that the whole sequence here and here are mapped. That means whole input sequence is mapped to, sequence 1 is mapped to sequence 2. Whole sequence is mapped. Okay, and the fourth one is slope constant. What is slope constant? So if you don't have slope constant, what happens is you will have things something like this. You have to start here and end here. That is fine, but you will have something. Okay. Yeah. So what in these specific regions, what happens? So many parts here, or rather many parts from this specific feature vectors are mapped onto the same feature vector. So, or almost the same feature vector. So here the range is more and here the range is less. So it inhibits the uh, diversity. So the slope constant avoids short to long mappings. And if you have such mappings, then you may not be able to get a proper warping function. That's why we avoid that. So for this specific question, they are asking which of them does not omit the important features. The answer is continuity. Okay. Any doubts?
No, sir.
Okay. We'll move on to the next question. So an iterative localization procedure based on maximization of a similarity measure is called what? So there are two things. There is iterative localization and there is similarity measure. So we have to make sure that we are using these keywords when deciding the answer. Okay. So before that, anyways, as usual, we'll check each of the options. What is blob tracking? So as we discussed, blob tracking means we'll check for one in the current image, we get some blobs and we'll check the specific objects that were detected in the previous image. And once we check, we detect a specific object in the previous image, we use that object and see which blob matches. And if both in both the ways it's the same correspondence, that means we are able to use the blob tracking for tracking the object. So here there is no measure of similarity. So okay, so this has no measure of similarity. The next one is kernel-based tracking. What do we do in kernel-based tracking? It is like the mean shift algorithm. So in mean shift algorithm, you have a similarity measure, which is the kernel. So once you have that kernel, that means you're using the similarity measure. And based on that, you find the mean vector over which you want to move your centroid of the region. So it has similarity measure and it's an iterative procedure as well. Blob tracking is not an iterative procedure. Okay. Similarity, not iterative. It has kernel and it is iterative. Okay. What about contour tracking? Contour tracking is not iterative and not using a similarity measure. You just track contours based on the neighborhoods and not really the similarity measure. And visual feature tracking is the feature-based tracking that was discussed. So for instance, you use information like color or the different parts of the object to track the object. It is not iterative again. You might use some similarity because you're using colors, but it's not iterative. So the final answer should be kernel-based tracking, since it uses similarity measure and it is an iterative. Okay, okay, then we can move on to the next question, I guess. The technique used for background subtraction is or what? Frame difference? Is it a technique for background subtraction? Anyone? Yes, right. If you take differences of two consecutive frames, whatever is the background, that is always constant. So you can remove the constant part, which is the background. So that's why it's a background subtraction technique. What is the Gaussian mixture model? Yes, you can model each every pixel as Gaussian mixtures that we discussed in the early part of the session. And based on that, we update whether a specific pixel is a background or a foreground using the standard deviation, how far it is, how far the pixel is from the mean with respect to the standard deviation. What about the kernel density estimation? Well, kernel density estimation is the same like mean shift. So with mean shift, you can easily segment objects, as I said. If one part of the mean shift will, if the, for instance, if you use color for mean shift, one part of them will be on the same part in the feature space, and the other object will be, the background will be in the other part of the feature space. So given that, you can easily say that it can be used for, once you detect the background from this case, you can easily remove the background. So you can use the kernel density estimation for background. So ultimately, the answer is all of the above. You can use all of the methods, frame difference, Gaussian mixture model, and kernel density estimation for a background subtraction. Okay, is this fine?
Yes, sir.
We move on to the next question. So you have an input image has been converted into a matrix of size 28 cross 28. So input image size is 28 cross 28, and the kernel filter size is 7 cross 7 with stride 1. Stride 1 means, anyways, I'll explain with the diagram. So, what is the size of the convolutional matrix? So, what is the output size? That's what they're asking. Or rather, convolved matrix. So, what we have is some image like this, which is 7 cross 7. Oh, sorry, image is 28 cross 20. So, once you have an image, you are not given any padding. No padding is there. That means there are no zeros padded over the image to take care of what's happening. So what we have is the kernel of size 7 cross 7. So I'll place kernel here of size 7 cross 7. So this width is 7 and this width is 7. The center one will be, if we assume that this is 1 cross 1 comma 1, this is 4 comma 4, right? This should be the center, and this will be 7 comma 7. So what you effectively get, the final image is like this. Since you can place your kernel here, you can only move along the kernels. You'll move, you'll move, uh, you'll only be able to compute the convolution in this region. Once you are able to get the convolution in this region, so what is the effective size that we have after stride one? Stride one means the next one will be placed like this, and the next one will be placed like this with the center somewhere here. Okay. So what you are doing is you are just moving it with moving over every pixel once you are in this region. So yeah, what is your effective size? So you have lost what? Three columns here. You have lost three columns here. Yes. This is three, right? This is three. This is seven. Since this is 4 comma 4, 4 minus 1 is 3. You have lost three rows, three columns here, and again you have lost three rows here on the top and three rows here on the bottom. So if I see the size of the image, which is 28 cross 28, and if I remove 3 plus 3, which is 6 rows and 6 columns, what you have is 22 cross 22 image. So your final image size is 22 cross 22. That is the output image size. Is this fine? Any doubts in this question? So we are just trying to find the output of the convolved image. Since we don't have padding, our image size reduces based on what is the kernel size. And since the stride is one, we only lose uh, images only at the boundaries. Image rows and columns at the boundaries and no other place. Okay, I hope this is clear. Move on to the last question of our session. Turns out to be a programming question. Okay. So what is a thumbnail? Anyone knows what is a thumbnail? Well, it's originally coming from our thumbs. The nail on the thumbs is called a thumbnail. That's how this name for in the image processing came. That if you want a very small image, representative of the bigger image, you call it as thumbnail. So whatever icons that you see are all thumbnails. Okay, so you're given an image. Uh, Image size is 1920 cross 1280. Once you have this, what we need to get is a new image of thumbnail 400 cross 400. Okay, so what should be the size of the new image? Can anyone tell? So the core idea is it maintains aspect ratio. So when you are maintaining aspect ratio, what happens is, since here you need to check it individually. First, you check along the row dimension. Initial size is 1920 and final size is 400. What this gives is 4.8, approximately 4. And what is given you among the column dimension? So it gives you 3.2. Yes. So along column dimension, you have this 3.2 factor. These are the factor of scaling along each dimension. But the final image, so these are the different factors of scaling. The point is, if you scale it with these specific factors along row and column, the aspect ratio will not be maintained. So what you need to do is take the maximum of this so which is 4.8. So what you do is your final image will be 1920 by 4.8 cross 1280 upon 4.8. Okay, this divided by this and this divided by this. What it gives you is this is uh, this should of course be 400 since we divided by 400 to get 4.8, and the last one should give you 266.66. So this is nearly 267. So your final answer is 400 cross 267. This is the image size, thumbnail size. Okay, is this question clear? So yeah. Okay then. This was the last session for the course. Thank you all for joining constantly for these sessions. I hope it has helped you to some extent to understand the course properly and help solve the problem. Okay.
Yes. So I have a doubt,
Mm-hmm.
but not today's assignment.
Okay.
Assignment number 5,
Uh,
in which there is one question to find the gamma correction.
okay. I
Yes, sir.
have done this question in the discussion 5. You can just go through that. I've done this question on Gamma.
Okay, sir.
Yeah, you can just check
Okay,
the
I will
video.
check that.
Yeah.
Yes, sir. And the another question is from assignment 10, question number 8. There is one question to find out the principal component.
Mm-hmm.
Yes, I know the how to solve the this particular problem, but not getting the answer which is mentioned in the options,
Okay, okay. Yeah,
and
PCA we
no
have done
detailed
similar
solution
questions.
provided.
Yeah, yeah.
Yes, sir.
So PCA we have done similar questions. You can just follow the same procedure. I mean I think you are also solved it the right way probably. You can just check your answer. If it's not matching, you can just post it on the forum because
Yes, sir.
I am not designing the questions, so I cannot really say whether that's the correct answer. Okay. Anything else?
No, sir. Thank you.
Okay. Thank you very much for joining the course. Okay. Good night.
Thank you, sir.